Hello everyone, my name is Balázs Vas and I am an assistant lecturer on the Budapest University of Technology and Economics. And I'm now going to present you our paper titled Polynomial-Time Algorithm for the Regional SRLG-disjoint path problem. Let me share my screen. My co-authors are Erika Renata Bérci-Kovács, Ábel Barabás, Zsombor László Hajdú, and János Tapocei. They are affiliated with my university or at the Eötvös Loránd University, which is also located at Budapest, Hungary. And I'm also part of the EIT Digital Industrial Doctoral School. Some words on the prior works. The abbreviation of SRLG stands for Shared Risk Linked Group. That is a set of links that are expected to fail simultaneously. For example, here the disasters are these colored regions, and the SRLGs are the sets of links which are hit by one disaster. So these two links are part of the same SRLG, but this link and this other one is not. In this study, we will suppose that a list of SRLGs is given as part of the input. So it is pre-computed. Computing SRLG disjoint paths is NP hard. This is kind of a common belief. However, hard instances are very artificial. So there is the question that, is it really hard to compute SRLG disjoint paths in the real life? We know that computing link and node disjoint paths is easy. And there are two Infocom papers which showed that if the topology is a planar graph and the disasters are circular disks with fixed radius, then there is still a polynomial time algorithm for computing a maximal number of disaster disjoint SRLG disjoint paths. A newer paper showed that the worst case failures in this model, the worst case places are few, and this can be seen as a cause of the easiness of the problem of this solvability in polynomial time. And here comes the question that could we generalize this problem such that it is still solvable efficiently? So here we come. An intuitive statement of the problem would be that we have a planar graph G as input. We don't have to know its exact embedding. This is a US topology with an example embedding. We have a set of connected disaster regions, these colored regions, and we have to find a maximum number of source target paths that are node disjoint and disaster disjoint. And here, the blue and the red paths are disaster disjoint, node disjoint, and on the other hand, disasters S1 and S2 separate together S from T, which means that there are no more than two disaster disjoint paths, SRLG disjoint paths. A more formal problem statement would go as follows. Before that, we call our problem as the maximum regional SRLG disjoint path problem, or MRSDP. So the input is a planar graph G, one of its duals. The dual of a planar graph is something like that. For each face or region of G, of the input graph, the primal graph, there is a node in the dual, and every face which have a common edge, neighboring faces, are connected by an edge in the dual. So each primal edge has a dual counterpart, and we suppose that we know that no rejection between these two edge sets. We know which is the dual edge of a primal edge. We know the source and the target nodes, and we have a set of dual connected SRLGs, including the node failures. Here, a dual connected SRLG is just a set of links which are touched or hit by a connected disaster region. For example, this edge, this one, and this third one are part of a dual connected SRLG because of this disaster S1. We can see that the duals of these edges form a connected subgraph of the dual of G. And this is why we call these kind of SRLGs dual connected. We can see that this notion of dual connectedness is really just another way of saying that the SRLGs are regional. Of course, our task is to find the maximum cardinality set of pairwise SRLG-disjoint ST paths. Our main result is that this problem is solvable in polynomial time. More precisely, if the number of SRLG-disjoint paths is k, then the number needed to compute these paths is squared in the number of network nodes times k plus the number of SRLGs, and this needed to be multiplied with a polynomial function of some parameters, where the parameters are the maximum size of an SRLG, the maximum number of SRLGs containing a given edge, and the maximum diameter of the dual of an SRLG. We think that in real problem instances, all these parameters are relatively small. And also this polynomial function is at most squared in each of the parameters. So no big exponents and no big parameters here. The proof of correctness of our algorithm, which we used, is based on a min-max theorem, which is similar to the classic max flow min-cut theorem for network flows. Here the max flow would be a maximal set of SRLG disjoint paths. The min-cut would be a minimal set of SRLGs which are separating S from T. The max flow min-cut theorem is a little bit weird because the min-cut could be max flow plus 2, and this theorem is tight. For example, in this story graph with these disasters in color, there is at most one disaster disjoint, SRLG disjoint ST path, while we need at least 3 SRLGs to separate S from T. A way of proving that there are no 2 paths which are SRLG disjoint here is related to a dual walk along these disasters, SRLGs, but I don't want to go into details. It is written in our paper how to construct these kind of proofs of the max flow not being higher than a given value. Time to speak about our algorithm. So the main step, the induction step of our algorithm, is that we have a number of k SRLG disjoint paths in this order around S from 1 to k, and we are searching for one more of them. For this, we generate a bunch of new paths, more precisely as many of them as the number of faces of the input graph plus 1, in such a way that each consecutive k paths are SRLG disjoint. And well, if this sequence, we have a subsequence of k plus 1 consecutive SRLG disjoint paths, then we are lucky. We can return with them and search maybe for even more SRLG disjoint paths, or else we can construct a witness, a proof of not being k plus 1 SRLG disjoint paths in the graph. Okay, how to construct a new path, PL? Well, it has to be SRLG disjoint from PL minus 1, from the previous pass, and it has to be rightwards from PL minus K plus 1. This rule is kind of explained here. Here, this PL minus K plus 1, sorry, is kind of unzipped, but you can think about it if it was just one pass. Here, PL can be calculated via a depth-first search, starting from the first edge of PL minus K plus 1, and exploring the edges incident to each node according to clockwise direction. And then PL will be just the ST pass in the DFS tree. So it can be calculated quite easily. In case of K equaling 1, when we are searching for two SRLG disjoint paths, things get a little bit more complicated. I don't want to go into details. See the paper for that one. Okay. On the evaluation, we use real backbone topologies as input graphs, downloaded from the topology zoo. We generated input SRLGs based on different kinds of disasters, disks with different radii, ellipses of similar size. Again, circular disks which are maximal such that they don't contain any node, or they contain at most one node. And finally, some random dual walks with length 2, 3, and 4. Here, all the numbers are averages. In the first, second, and third column, we can see the minimum, average, and maximum diameter of the SRLGs in average. Here we can see the minimum, average, and maximum number of links which are part of the SRLGs, and in the last column we can see the average number of SRLGs which were generated in each of these settings. We implemented our algorithm in Python in NetworkX. The source code is available at GitHub. It outputs XML files, super easy to work with it. So please just try it. And some runtime results. So we measured runtime on a commodity laptop. We not really optimized for speed, but we can see that even for our biggest graph, which has almost 400 nodes, the runtime was not exceeding 100 seconds. And in the smallest graph we investigated, it was below 0.01 seconds. The runtime was quadratic in the number of network nodes. Here, the y-axis was logarithmic. Just a note here. And we can see that there is kind of an additional complexity in the maximum diameter of the SRLGs, which is denoted by D. We also investigated the stretch of the SRLG disjoint path compared to the shortest path. We saw that on average, the shortest among the SRLG disjoint paths was on average 4% longer than the shortest path between S and T. So it makes a good candidate for the primary path. And the average and maximal path lengths among the SRLG disjoint paths were at most up to 2 or 3 times of the length of the shortest path. So it makes them reasonable backup paths for the networks. Finally, well, we can see that as the problem settings, the average diameter of the SRLGs is increasing, the average number of SRLG disjoint paths are decreasing. This is also can be thought intuitively, but here's also a justification for that one. And that's all. This concludes my talk. I'm happy to take questions. Again, our source code is available on GitHub. Please check out our paper and our source code and feel free to use it. Thank you very much.